if we look at the combinators post, we can say, okay, so that's plus and 2. Okay, so S of S of K okay, so here, this thing applied to nest of that applied to this. And then the whole point is that is equivalent to nest of S comma K comma 4. Okay. But the fact that that is true is derivable by saying what? Oh, apparently we have to have an S of K there. I don't know why. What the heck? Plus, which one is plus now? Well, okay, so what this should have done, which it didn't do for some reason.
Yeah, I get it.
What's that?
Yeah, I get it. Should be 2 plus 2. Number of S's is just your natural number. And plus is also a combinator.
Right.
Oh, by the way, yeah, Stephen, it appears as though this guy, John, found a simpler combinator for plus.
Oh, cool. Well,
Yeah.
we'll put it in. I mean,
Yeah, here, I'll fetch it. One moment. I've been reviewing his suggestions with Paige, and they all appear to be right.
I'm glad he found a simpler combinator for plus.
I mean, it's just shorter. Okay.
Oh, that's great.
Yeah.
Okay, why didn't this simplify? I don't understand what's happening here. What am I doing wrong? What the hell am I doing wrong?
Do you have to have a SK there again?
It doesn't look like it. Well, what's that? That's some different integer.
Huh. Yeah. or just thesis?
The hell is that? What the hell is that? What is that stupid creature?
Yeah, that's strange.
Okay, but I'm just trying to understand qualitatively what's going to happen here. So what's going to happen is we're going to start purely with the combinator relations.
Okay. Yeah.
And okay. Okay. Workflow. Start purely with the combinator relations. Then follow laws of inference. Okay, so the combinator relations, let's be specific, are this. Okay. Now the claim is that starting purely with these, or more specifically, we have to blankify this one. Okay. Start purely with the combinator relations, then follow laws of inference. Then we get equivalences that we can identify as being mathematics, basically, e.g. 2 + 2 = 4. But don't we also get lots of other equivalences that are just, we don't know what the heck they mean?
Yeah, sure.
That wouldn't be surprising,
Yeah, right.
especially at the machine code level, right?
Mm-hmm.
Yeah.
So is there any simpler thing than combinators with which we can build all this stuff? Let's assume not. Okay, next question. S and K here.
Do we need them?
Yeah, we probably don't need them.
I don't think we need them. Isn't the working hypothesis that X goes to X of X, albeit kind of slow, would suffice?
No, I don't think it'll work.
Did you think it would work yesterday?
No, I think it will generate every expression.
Yeah. Okay.
But I don't think it generates them. Look, we need to generate 2 + 2 = 4, but not 2 + 2 = 7.
Right. So 2 + 2 = 4 is it's in there for X goes to X of X, but so is a bunch of other junk.
Right. So is 2 + 2 = 7.
Yeah, right. So wait, you want to know the minimal combinator that just gives us the recognizable mathematics and no junk.
No, it'll have incomprehensible junk. But once we've identified what corresponds to an integer, it better only give us true relations about integers.
Okay.
Okay, let's figure out how to make this work.
Yeah.
What the heck did I do wrong with my integers there? Sure, this is an NKS, so let me look for that. What did I do wrong? This is crazy. Okay. Oh, that's a successor function there.
Yeah, that was.
We
there
can
in the
decode
integers.
by applying to S of K.
Yeah.
Okay, so basically what we have to do. Well, that's very bizarre. So we have to apply S of K on both sides here. Oh, so this is in fact not the right thing to do. Okay, so okay, but the main point is that what we're saying is, given a particular initial set of axioms like these ones, okay?
Mhm.
Okay, so for example, we should be able to get a proof, e.g., we should be able to get a proof that 2 + 2 = 4 in terms of the SK axioms. You see what I'm saying?
Yes.
Mm-hmm.
And ultimately, it will be something that we could just unravel. In fact, that proof, in this case is just the computation. That's all we need for that proof in this case.
Good. Well, that's a nice constructivist approach. Yes.
It's just running the computation in this case,
Mhm.
except we'd like to get it right.
Well, otherwise it's not a very good proof.
Okay, well, let's just write this out. So where's plus?
Proof is always a computation, right?
Yeah, I know, but
Or is it only in constructive logic?
well, hold on. Let's just see the proof of 2 + 2 = 4. Okay, so there's that. Let's do 2 + 3 = 5.
I also included the other addition combinator in the chat
Okay,
in case you're interested.
okay.
Is it like for same integers? Or it requires other encoding?
Okay, let's do this. Oh, come on. Why aren't those the same? Well, maybe what we have to do is say this of S of K. It's kind of hacky.
Mm-hmm.
That's rather horrifying. Okay, well, I'd like to get a better representation of plus.
Okay.
But I mean, I mean, this is still a workable thing. This is saying this is our theorem, basically. That's our theorem. Ground into machine code of such unbelievable minimalism.
Yeah.
But that is our theorem, that 2 + 2 is 4.
Okay.
And the proof,
Yeah.
let's show the proof. I mean, the proof,
Yeah, we can do that.
let's actually look at all proofs of this, okay?
Mm-hmm.
So
You already have a proof. The proof is the constructed expression.
I know.
You
But
just
he wants to
take
look at
away-
all of them. Yeah.
No, I'm saying let's look at in here. Notice that in fact, okay, we're also going to do an actual proof with the proof object. Okay, so here, that mapped over this guy. What? Multi-way combinator.
Oh, you're mapping over each one. Okay.
Hmm. Mhm.
You just map operator has a higher.
What's that?
Map operator has a, how to call it? Basically, it applies first rather than two-way rule operator. Precedence, yeah. Map operator has a higher precedence.
But we should also be able to apply the rules. This is applying the rules from the outside, but we should also be able to apply the rules inside to the whole thing. You see what I'm saying?
So
Rulegenic.
What's that?
You mean to derive more rules?
Yes.
Make it rulegenic evolution.
I like that term. Yeah, rulogenic. Right.
Okay, let's see.
Now I don't know if this is the right time to mention this, but so before Stephen, when Nick and I, before you joined, we were investigating why it is that x goes to x of x and x of x goes to x to yield the same results. Nick concluded that there was some feature of multi-way combinator that
Yeah, well, it's probably wrong.
right. So, but Nick
it
has
looks like a bug.
But Nick had
Seems like a bug.
some new. I mean, it's very new, but he had some new function for it.
I think we're just trying to understand conceptually what's going on here.
Well, okay, but anyway,
Yeah, so it's
Just
probably
keep
wrong.
that in mind.
Right now. Yeah.
Yeah.
Oh God, how big is this getting? Well, this is saying, this is kind of going the other way around, right? Okay, this is kind of going the other way around of but what I'm saying is start from those combinator expressions and now just find true statements of the combinator world.
Yeah.
Right? And somewhere in there will be arithmetic. Along with every other axiomatic system. No. What else will be in there? Will every other axiomatic system be in there somewhere? I think it will be.
Oh, yeah, it means that S and K are universal, right?
Yeah.
Right, essentially.
Yeah. So starting with the SK rules, we can derive relations for any axiomatic system. Now, in a very Rulliad-like way, there's an issue because we could derive ones for the whole point is what gives it real content is the fact that given a particular axiom system, we can then derive an infinite number of things for that axiom system.
Mhm.
Given a particular identification of meanings, we can derive an infinite number of theorems, of statements right we can derive all statements that involve those subtrees. Right. So in other words, what we're saying is meanings are equivalent to certain subtrees. Meanings / operators are equivalent to certain subtrees. Okay,
Do
so
you think
then
like just the structure of trees or like a relation to other trees? So
I think the
position.
structure of trees is enough. I think. I would guess.
I actually think it's not enough.
Okay, well,
I think
anyway, let's just keep going for a second. So the claim would be that we can, quotes, observe certain combinator relations
Mhm.
by reducing them to, quotes, understandable form, e.g., to be specific, is plus of, well, successor, whatever it is, nest successor. I don't know what we start with. I mean, we can just say plus of 3 and 2 is equivalent to 5. That's our identification. And then we should be the case that if we do that, then we should also generate, for example, plus, well, using the exact same symbols, plus 3, 2, 3, 2, 2 is equivalent to plus, actually, let me make this more complicated. 2, 3, 2 is equivalent to plus of 5, 2, or 2, 5, let's say 5, 2, whatever we want. Okay, well, then we should also generate that purely by just machinery, purely by just applying the machine code.
Mm-hmm.
And we should not generate right-hand side plus of 18, 2.
Right. Yes.
Yeah, if you made identification correctly, right?
If what? If we made
If we
the correct
this, yeah, if we made identification with combinations, that it's actually a correct plus. We still can like encounter some kind of contradiction later.
But the question is whether or not those incorrect statements really persist with time, or whether or not they kind of fall apart. They don't actually advance very far.
Right, well, that's the question of, is it a natural definition of plus? In other words, there will be certain, right, the basic claim is there will be certain definable things that survive,
Yes.
quotes, proof evolution.
Right. Yeah, they have like proof fitness or something, right?
Yeah.
Some quality that allows them to persist.
This is a weird view of mathematics.
I like it. Yeah.
Mathematics, this is
well, it's a weird,
that's naturally occurring.
Mm-hmm.
This takes the point of view. Okay. So the human observer of mathematics, there's a soup of combinators, let's say. The role of the human observer of mathematics is to identify, this is what the observer does, is to identify these lumps and give them names.
Yeah.
Right.
Having done that,
Mm-hmm.
there's then this ocean of sort of proving that happens.
Mm-hmm.
And somehow there are identifiable pieces, but those so for example, we can ask, what are the proof chains between identifiable pieces?
Sure.
We should make a library of theorems using combinators underneath.
Yes.
Yes, I mean there's much archival, rheological, and experimental work to be done here. I mean, I'm interested in it, for instance, in testing the kind of fitness of basically of mathematics that we end up not including, and why is it that it doesn't, why it's not observed? Basically, as kind of there's like a selection effect based on proof fitness, or the ability of certain entailments to persist in the mathematical space.
Yeah, but also there's going to be things which are okay. So one issue is certainly there'll be certain definable things that survive brief evolution. Okay, so then for observers like us, yeah, the point is, for observers like us, we need identical objects to reoccur in the proof evolution. Otherwise, it will be okay to get different objects if we were non-persistent observers.
That's a peculiar statement.
In other words, the fact that we need identical objects is a consequence of the fact that we believe in some kind of permanence.
Right. Yep.
Otherwise, we could just say, that's fine, plus is something different later.
Well, the point is that if we could tolerate that, we really wouldn't be observers.
Right. If we are to be consistent observers,
like persistent.
Well, consistent and persistent observers.
Okay.
Essentially with bounded sort of model finding / computation capabilities, we need consistency in our decoder function that identifies, plus from the soup of combinators. Okay, so what we're saying here is you've got this
enough to prove something about plus in order to identify it, and not consider every step of evolution further. So as soon as you prove any axiom about plus, you don't have to.
Well, let me remind you, we could prove the Peano axioms, but that wouldn't actually show that it was plus about integers. Right, because that's okay. So what we're saying is, okay, to establish that a particular combinator lump quotes is plus, show the Peano axioms for it. Though this isn't quite enough. I would still say we consider that to be plus. But eventually there will be theorems that aren't what we normally think of as theorems about plus. There'll be plus for non-standard arithmetic and so on. Does that make sense?
Is it like a plus can be multi-purpose? So maybe, yes, we proved Peano axioms for plus, but further for the same combinator, you can prove something else. So
yeah, well, I mean, you can add a large cardinal axiom, for example. In other words, you can prove one of the things that will emerge, all the different forms of non-standard arithmetic the theorems, okay, the theorems of all possible non-standard arithmetics will also show up in the combinator soup. So we could have a different identification for plus in the combinator soup. Let's see.
So we would actually have like different classes if they have like on integers and on real numbers. How would they identify those?
Well, they have different
the
accents.
same class.
They're not the same plus.
Then why we call them both? We call them plus.
Because they satisfy more or less the same axioms.
So it's like the structure of axioms defines the plus. How we define them, human.
I think so. Yeah, but I mean, okay, hold on. What we're saying is, okay, zooming out again for a second. Our fundamental model is the statements of mathematics. I won't say true statements. Statements in mathematics are derived by a rulogenic or non-rulogenic process from certain initial relations using laws of inference that make use of the structure of these things. And the laws of inference might care most about ones which are rules, because those are applicable. You know, those can be applied to other ones.
Sure.
Okay, but in the end, we're going to derive this giant soup of statements. Some of those statements we will identify as human mathematics. Few and far between.
Right.
Oh, I see. But the claim is that there are some global laws of this giant proof soup, so to speak. At a high level, we don't need to go through the whole proof soup. We can just,
well, that's the kind of hypothesis, right?
Right. High level mathematics is able to make quotes reducible jumps between recognizable constructs in the ocean of statements. And I mean, okay, how is that like fluid mechanics? In fluid mechanics,
well, you don't often care about the molecular dynamics. That's the point.
No, I understand. But the thing is that what we've got is tracer particles here.
Okay, go on.
Yeah, okay. So recognizable statements are like tracer particles in fluid mechanics. That is, i.e., you can describe their motion even though they're just point particles. You can describe their motion in terms of fluid behavior without going down to the molecular level. So you can say things about the relationships between these tracer objects
Mhm.
in the super statements.
Mhm.
And for example, you can probably make some relativistic statements about that because let's see. We had made a bunch of statements here. So by the way, I mean, this is a representation of a very high level. Both of these are fairly high level relative to the underlying combinators, although
Mhm.
well,
But in principle, you can look inside each
yeah,
of
you can compile it down
Yeah.
to something which won't quite be combinators, but it'll be something quite simple. It's expressions. See, the thing I'm confused by in metamath is, in the end, you compile it down to the axioms.
Hmm.
But don't you introduce a bunch of named things?
Yeah. Yeah.
But each named thing has an axiom associated with it, doesn't it? I mean, to define plus, you introduce axioms of plus.
Yeah.
Okay, but that's not what you're doing in combinators. In combinators, you're saying you start off from something completely uniform.
Well, right. I mean, metamath doesn't seem like it actually pierces to the machine code level, really.
Gets close.
Because humans kind of assume that something is behaving on the lower scale somehow and just hopes that it's true, right? But maybe, and when there is a contradiction, maybe that only means that there is no combinators that actually it can be compiled into.
Yeah, but I mean, in metamath, you're introduced an axiom that involves plus. So that's how you introduce the term plus.
Sure. Yeah.
Okay, so we've got really two cases. Explicitly introduce new quote symbols, e.g. plus, by having axioms, by having statements that reference them. Or two, have these things arise naturally and then identify certain lumps as plus. Okay, so one case, we're kind of going much higher level by introducing those symbols. But we imagine, and this is kind of the conceit of the Rouliad, so to speak, we imagine that everything could be gotten by natural occurrence.
Natural occurrence.
Without having to introduce the named thing plus with its axiom.
Yeah.
We just bubble it up and eventually we say, look, there's a plus floating by.
So you mean entailment from the machine code level?
Well, it's not entailment because the issue is when we see something floating by, is it plus? Well, if we named it plus ab initio because we introduced an explicitly named axiom that has a plus hanging off it,
Right.
so be it. The other possibility is it's just this blob of stuff that we say, look, we can naturally identify that with plus, it will have the right axioms.
Right, but that's something that we can identify because it survives entailment.
Oh, I see what you're saying. I see what you're saying. If it doesn't survive entailment, all bets are off.
Yeah.
Right. So it has to be a persistent object of some kind.
Yeah. And the persistence is over entailment.
Yeah, that's correct.
And that entailment in our case begins at this machine code combinator level.
Isn't like everything is persistent in this kind of model? Anyway?
Everything what?
Anything is persistent because you can always start from scratch and derive it.
But sometimes you don't get anywhere. It depends on what your, right? What your pattern is, what your rules are.
No,
No?
if you have just two rules for SK combinators, those are just two rules that we have. We start from those, and we can derive a bunch of other terms. So anything that we derive is persistent from this point on. It's not getting destroyed or anything.
Yeah, that's a fair point. I mean,
Yeah.
it can reoccur. With those particular rules, it can reoccur.
Yes, I mean this idea of persistence is still quite vaguely defined. That's why I said before
Okay,
something of
okay.
interest to me.
Given
Yeah,
this,
studying it in
given
more
this
detail.
thing, in the entailment structure, we can take a branchial slice, and we can say, at this moment in the evolution of mathematics, what are our true statements?
Mhm.
There is some relativistic invariance in the sense that insofar as there's causal invariance, we can pick different foliations for current mathematics. Now, to derive a particular, well, one of the issues would be, oh gosh, I don't know. To derive a particular thing, do we have to go down to the molecular dynamics level, or can we hop high level to high level? Right, that's the claim of mathematics.
Right.
The claim of basic claim of the possibility of high level mathematics. We can jump from high level construct to another without having to go down to the machine code. Now, that might not always be true.
Well,
At the level of the machine code, there's tons of undecidability.
Well, not only that, I mean, it seems as though part of the motivation for the recent kind of interest in automated theorem proving and proof assistance is that if we take enough high-level jumps and it's difficult to test them or evaluate them, that we might be making some considerable errors mathematically without noticing.
Yeah, well, right. But I mean, if you take a bunch of high-level jumps, even a small error, look, with enough high-level jumps, even a small error can eventually derail you.
But the other point is that when you're at the high level, you might lose some. If you go astray, you might not have enough perspective to see where you want to stray, you know?
Yeah.
Right. I can't help but think of the like the people in Sao Paulo who take helicopter taxis back and forth because the traffic is bad and they don't actually go onto the street very often. That's just a metaphor that I think of often. So everything could have changed on the street, you know, and you'd have no idea.
Right. But we should probably wrap up soon here. But
What time is it? It's like 2 a.m. for Nick, I think.
is it that late? Oh, sorry again. Well, okay, just I'm still just trying to understand what can we learn from the metamath, kind of empirical metamath stuff.
Yeah, Nick, what's your take on this after our kind of exercises of trying to work with metamath? How would you compare it with what we've been doing since and lessons we can derive from it?
Well, that's still very similar. Just like defining anything in MetaMath is just adding one additional tool rule in our what of rules, right? When we actually name stuff somehow and abstracting our low level stuff into high level, and you can do it indefinitely, and you can just the difference is that you can add a rule that is inconsistent, because you not always have a way to derive it with the low level.
Right. You can add random rules. Yes.
Yeah.
Now, I mean, in something like lean, do you imagine that you derive everything from, I mean, look, doesn't metamath have the idea that there's some stuff you can just derive from set theory?
Well, they use set theory.
Yeah.
No, I understand that, but do they also use additional definitions?
Oh, sure. There's like some meta stuff there is required.
No, but the definition of plus, there's a thing named plus and it has certain rules. It has certain statements about it. And that's how they introduce plus, isn't it? Plus is not emergent.
Well, it's a definition anyway. The definition is kind of not required to be proven. It's just theorems about plus. That's what requires to be proven. You can define the plus.
I know. But I mean, it's like saying there's an emergent plus. But the issue is whether that emergent plus somehow survives well under entailments. I mean,
it's not clear to me if it's really tested in that way, though. Tested in a way where it would even be in a position not to survive. Because it seems like it's just kind of included.
Yeah.
In the statements, you know?
Well, not surviving is probably equivalent to very few things can be proved about it.
Very few things can be proved about plus in metamath. Well, but that might actually be true. Would that be true? Because what is proved about plus in metamath?
Probably all kinds of things.
Yeah, everything.
Well, but is it about plus, or is plus just used to make proofs about other things where they're the actual focus of the proof?
No. Plus, there will be, once you've introduced a statement about plus, you can derive other statements about plus. Once you've introduced a statement that syntactically contains plus, you can derive other statements about plus.
Okay, you can look at it that way. I see. Fair enough.
But you don't really need to introduce, a notion of plus. I mean, this is very much like Whitehead Russell in the sense that they wanted to start from, or Frege, start from logic for everything.
Mm.
And then say, look, here we have this thing made from this same machine code. mean, the fact that, okay, the fact that we can define standard math uniformly in terms of something computational is what the existence of WL proves.
It's a good advertisement.
Right.
Yeah, send that to marketing.
Right. So the thing we call mathematics can ultimately be ground down to this purely computational substrate, this uniform computational substrate, which could be combinators, could be all kinds of things, could be the Roolead.
Can you grind down to the Roolead?
Well, why not? With some representation of the Roolead, with Turing machines or whatever else you haven't, it's making Roolead. That's just some representation. You can grind down to a slice of the Roolead or a coordinatization of it.
Yeah. Okay, fair enough. Not the whole thing.
Right.
Yeah. Okay. It's fine.
Okay. So this comes back to what I looked at in NKS, which is which axiom systems actually occur. I mean, this is then the quotes lumps that represent, identifiable math. That's very much like the NKS study of possible axiom systems. By the way, the generalization of that is just, let's say we have a binary operator. Yeah, it's exactly the same thing we've been looking at. I could turn those things into combinators. I could have it with binary operators. It doesn't really make any difference. I don't know what the operator is. What is the general operator system? Just like
Well,
I don't know,
especially
I
at
think
this
any one of them.
combinator level, we don't even really have operators, do we?
No.
No, it's slimmer than that.
Yeah.
Yeah. Which seems right.
Yeah, I agree.
I mean, we might not even need S and K. The less we need, the
No, we
happier
won't
I
need.
am.
We eventually won't need S and K.
Right. It will take some experimentation, but right. We won't need
Well, what will happen is, I mean, the other question is that why are we bothering with something which has this tree structure of mathematics? That's to make it easier to make the identification with ordinary mathematics. We could as well just represent everything in terms of hypergraphs, for example. Just that's not such a convenient representation of mathematics, I think.
Right. Well, would it be expressive enough?
Statements in MetaMorph is just sequences of constants and variables, so it is a hyperedge, not a tree-like structure.
Well, that's a nice comparison.
Okay, but then if that's the case,
yeah, we have to have a way to actually have something that produces those hyperedges. Proofs are still tree-like that evaluated into those hyperedges.
All right, but the basic claim, the reason that high-level mathematics is possible has to be the same as the reason that our perception of space is possible. The existence of high-level mathematics is the same as the existence of high-level physics, it's claimed in this model. And what else can we say based on that fact?
Well, we can make all the claims we've made about observers and persistence.
Yeah.
Yeah,
But
I mean,
then,
much of what we've said so far and in the other notebooks is consistent with this idea.
yeah.
Yeah.
All right, we should probably wrap up.
By the way, Stephen, as a kind of meta methodological note, what do you do with all these notebooks?
They're sitting on the public file server. I mean,
No, I know, but like we have, well, we won't. I imagine when you write the blog, you're not going to refer to necessarily all 21 of these, but like since notebook 17 or so, maybe 16, these notebooks are quite rich, quite, right? So
yeah, I know.
So
I
what
know.
do you?
I
I mean,
know.
just so I understand. I mean, so you. Take
I
all
don't
these
have
notes.
a great procedure. I mean, I look through this and I try and get into some state where I can start writing things. And usually what happens is, eventually the concepts simplify to the point where, and this is getting pretty close, I think. I mean, the difficulty is how much of this, the explicitness of compiling everything into combinators will be only partially useful because it will get way too complicated way too quickly.
Well, you can give a simple example.
I know.
But then we have many other tools for computing and visualizing this. So
I know. I mean, the basic structure has to be, this is the qualitative picture of what mathematics is. Now here's how you actually make a correspondence between this low-level stuff and so traditional mathematical stuff. Then once you do mathematics in bulk, including all the meaningless mathematics, so including all the mathematics for which we humans have not yet identified any interest. But the difference between ruleyology and this is that in ruleyology, every sort of, here we're attempting to identify sort of a high level, we're trying to look only at certain observable things and ask questions about the observable things rather than go all the way down to the machine code and ask questions about what happens at that level. So the issue again, what counts as an observable thing in mathematics? And what we're seeing is, and how do you, from the soup of combinators, how do you say, yes, that thing there is going to be a part of human mathematics? And my guess is that the mathematical observer has some non-zero extent in meta-mathematical branchial space, so to speak.
Well, I wouldn't be surprised by that either. No.
Which is to say that it's the Pythagorean theorem plus all little fluffy changes to the Pythagorean theorem that still count as the Pythagorean theorem.
What, the Pythagorean halo or what have you? Yeah.
And that in other words, when you try and be overly precise, you could do that purely at the machine code, single statement to single statement. It's kind of like the Pythagorean theorem at machine level is really the Pythagorean cloud. Because humans don't care about those micro details. Don't care about whether, about e.g., the precise axiomatic structure of the reals and defining the Pythagorean theorem. So the issue then is whether as you go and do things on the basis of the Pythagorean theorem, do you get shredded? Does that thing that seemed to be just the Pythagorean cloud wind up all going to the same place, or does it get shredded into lots of little pieces?
But is the claim that most of the time, if you've identified some cloud with some familiar mathematical object, that you won't get shredded? That's kind of why you've identified it.
That's the claim. That's the claim. That's the claim. The claim is that, yes, the claim is that the cloud is puffed out by computational irreducibility.
Yes, we name friendly clouds, so to speak. This is the point. Yes.
Yeah.
Unfriendly clouds, we kind of avoid them, and they're shredding.
Right. Once
yeah, right.
Once we have one of these things, it doesn't now, that theorem cloud for the Pythagorean theorem is probably one way to see it is in different proof assistant systems with different axiom systems, you still get something that you call the Pythagorean theorem.
Well, that's, yes, more specifically, that's what it means, right? Is that you can obtain something like the Pythagorean theorem, or that could be identified as Pythagorean theorem via different machine paths.
Right. Then one question is whether the question of quantum mathematics.
Here we go. Yeah.
Is a question of whether it matters, whether you have to go below the high level version.
Yeah. Right. Nick, any insights from the quantum framework that you want to?
No, I don't think it's that.
No, but Nick has just been thinking about, quantum mechanics, and he's involved in this project.
Well, I know, but I think that the point here, as I kind of say, that oh gosh, what was I going to say? Oh, I lost it. Anyway, but yeah, if you can stay. I'm still trying to understand what is the, like, for example, okay, yeah, right. So actually it is worth asking about the quantum mechanics case, because it's kind of like what's the no cloning theorem here?
Here.
The no cloning theorem in quantum mechanics is you can't step in the same river twice. Once you have this multi-way graph, every place in the multi-way graph is unique.
Okay. Yeah, correct. So quantum mechanics is like additional constraint, right? Described as constraint on some other, like on linear algebra, right?
Well,
and no cloning theorem is one of those constraints.
That's one way to look at it, very much in terms of the traditional formalism. But
Well, not just traditional, even modern one. Even like
Yeah, I understand.
diagrams and string diagrams.
right, which we also need to understand. All right, I should go.
Are you going to see a film?
No, I don't think so. I think I'm not sure what I'm doing, except that I'm really tired.
Yeah, I think
And-
we're all tired, or
Oh.
I'm tired. Nick?
Well, okay. Well, it's very late for Nick. All right. Well, I think then. All right, we got a few things here, and I think we need to absorb this a little bit. We need to clean up some of the things that we don't really understand properly. I think we made good progress on this co-substitution business. That to me,
Thanks, Nick.
yeah, that to me is a big, that's one of the remaining. How is this related to kind of mathematical formalism?